Any aero device that produces lift, or its opposite, downforce, also produces drag. The ratio of the two, L over D, measures how efficiently lift is being generated. For commercial airliners and crews, this value is 15 to 20. For sailplanes, it can be over 30. But the likely LD of early winglets was poor since much of the airflow spilled over their wingtips, maybe just 3. To minimize these tip losses, subsonic wings are made long and slender. Aero devices were especially attractive to Ducati because they needed a new technology to break out of a long period of mediocre results. They had excess horsepower that could be used to push downforce devices through the resisting air. And their fundraisers had a history of success. For safety, the next generation winglets were made in vertical pairs with their tips joined by a vertical member, making them look like handles. In the early days, these handles became a Ducati signature, but recently the upper ones have evolved into ducts with outlets aimed upward. The other major downforce design originated with Aprilia and is now part of Yamaha's new-look fairings. An array of 2 or 3 airfoils is attached to the chin of the fairing nose. It is high enough in the center to clear the front tire under full compression, but droops downward on either side like a comic mustache. Total width is regulated, as is how far forward aero devices can be located. So why use multiple airfoils with slots between them, rather than a single wide-chord foil? The slots allow higher pressure air to flow onto the lower pressure surface of the next airfoil behind it. This energizes its boundary layer, postpones flow separation, and increases lift. These arrays are seen on the noses of F1 cars, and if you're seated behind the wing on your next commercial flight, you can see them during landing as part of the multi-element flap system.